later. All right. Okay. And by the way, the recorded lectures are also available online on the course website. So you don't necessarily have to look at my face. Okay. Now, so what we'll do is we'll finish TLB coverage in Superpages, and then if time permits, we'll go on to segmentation. Before I start, one of the questions you may have in mind is, one of the students asked a question about midterm exam. I had mentioned, let me go back to the, if you can see my shared screen, we had this test scheduled on March 23rd. At the present time, it's safe to say that we will not have a test on March 23rd. So I will update that. Instead, I'm still discussing with other colleagues, what's the best way to proceed with whether to convert that test into an assignment or whether to have some other kind of test. So once I come to a decision, I will communicate that with you. But right now, I just want to let everyone know there will be no midterm on March 23rd. Okay. So in the meantime, do work on your assignment too. It will be due on March 27th as was originally planned. All right. Let me see if, okay, so there are no questions. So now I will switch to the slides. Let me go to the slides. All right. And so again, I will briefly summarize where we were last time, and from there we will go on to the details of TLB coverage. So we had started with this idea that TLB, or translation look-aside buffer, is important for improving the performance of MMU, or memory management unit. Right? MMU needs to translate virtual addresses to physical addresses. In order to do so, it has to refer to the page table. Now, page table is present in the main memory, so you don't want to go to the main memory very often. So as a result, we take some of the most important entries of the page table and we keep it close to the MMU in a small cache, a translation cache called TLB, or translation look-aside buffer. So the idea here was the larger the TLB, the fewer times we have to go to the main memory to look up page table entries, right? So we can avoid page table walks. So if we have more entries in the TLB, we can store more virtual page number to physical page number mappings. And as a result, we don't have to go to the page table anymore as much as we would have to. So so what has happened over the years is that the memory usage of applications has gone up, and in the meantime, the TLB size has not kept pace with that. So as a result, we're having more and more TLB misses. So in order to increase TLB coverage, various processor architectures have had this ability to support something called superpages, or large pages, where you could use one TLB entry to translate a virtual to physical page number for a large page or a super page. And by doing this, you don't have to increase the size of the TLB. You could simply you choose a larger sized page and get better TLB coverage. So that's the key idea behind TLB coverage, which is informally the amount of virtual memory mapped by the TLB, so this particular paper is about how we can have the operating system provide support for superpages to applications or user space applications without having to modify them. So we want the superpage supposed to be transparent. We don't want applications to know. Just like when you use virtual memory, you don't need to know that you're using regular pages. So similarly, when you're using Superpages, again, you don't want applications to know about it. And then we want to be able to use a mix of Superpages, large pages, small pages, and uh, and we want to be able to like use them when we want it, and we want to stop using them when we don't want it anymore, right? So all this has to be happen behind the scene without applications knowledge. Okay. um, I'm going to just find a way to keep an eye on the chat screen if somebody has any questions here. Okay. Any questions so far about what we have discussed? Okay. So back to the slides. You know, all right. So let me get rid of participants. Sorry, I'm still trying to figure out how to manage all the windows here. There must be an easier way. We will figure it out soon. All right, back to the slides. So, so we had seen some of the constraints on Superpages last time, which is that one was that the Superpages should be powers of 2 times the base page size, and we had discussed various reasons that should be so. We saw that the base pages in a super page, they have to be contiguous, meaning they need to be next to each other in both the virtual address space and the physical address space. And they need to be aligned in the sense that, for example, if you have a super page of size, 4 base pages, then your super page can start from virtual page number 0 or page number 4 or page number 8 or 12, but you can't have a super page of size 4 starting from, say, page number 2 or 3 or 6, for example, because those numbers are 2, 3, and 6 are not aligned at the super page size. Likewise, if you have a super page of size 8, then you can you can have them start from 0 or 8 or 16 or 24, but you can't have them start anywhere in between, say from 7 or 12, for example. So the other requirement was that they have uniform protection bits. All the base pages, you can't have some base pages having say read-write permissions, some other base pages having execute permissions, and then all the base pages share one reference bit and one dirty bit, all right? Because if you do, what that means is if you say write to one of the base pages, then all the base pages in that super page will be mapped as, will be marked as dirty. There will be no way for the operating system to distinguish which one of the base pages is dirty. So this is an important constraint, as we will see later down in super page demotions, in the sense that if let's say you have a really large super page, say 256 megabytes, as some super pages can be, and it has a whole lot of base pages. So if you dirty just one of those base pages, all of them are going to be marked as dirty, and we will run into problems. Let's say you have to swap out that large super page, and at that point, since you don't know which base page is dirty, you'll have to swap out the whole super page. So this is an important source of overhead, and this paper tries to address that issue as well. Okay, so any questions so far? I can give a moment for you to type any questions if you have. Okay, so I will go to the next slide. So last time we saw that, again, super page occupies one TLB entry. If it was a regular base page, that will also occupy one TLB entry. The difference between a super page and a base page would be that there will be some additional field in the TLB that would give you the size of the super page. that the MMU is trying to access, right? Uh, so a base page would point to the, give you the page number, physical page number of the corresponding page in physical memory. Similarly, a super page would give you the super page number of the corresponding page in physical memory, all right? With the understanding that any offset that follows would refer to the entire super page, starting from the base address. Okay. So, um, so here were some examples that we discussed last time. If you had the contiguity requirement that both the virtual and the physical pages have to be next to each other, and the alignment requirement that I just discussed. So I'm not going to go over these again. Uh, it's just for recap from last time. All right. So let's move forward. So super page problem, which was that, if we, so going back to our original problem, which is that operating system has to support these super pages for applications. Applications do their normal memory allocation and file access and all that stuff. And under the hood, OS has to figure out when does it allocate a normal page and when it needs to allocate a super page. So, and if it has to allocate a super page, what size should the super page be? Should it be just a super page of 2 base pages, or uh, 8 base pages, or whatever? So, uh, as we will see, there's a lot of guesswork involved. So here was the example that we discussed, where an application starts accessing some addresses in its virtual memory. For example, base page B in virtual memory is mapped to certain physical memory page. And then as the application accesses nearby virtual pages A, C, and E, they might be allocated all over the physical memory. And at some point, if we want to convert them to a super page, we may have to move all these scattered physical pages into one central location, which will then be marked as a super page. All right. Now, this copying overhead, moving scattered physical pages to one location, that copying overhead can be significant, especially if you have to do it very often. So, so there is the question of what time do you allocate a super page ahead of time, or do you wait and then move the pages later at a later time? The other question is about promotion. For example, here we have an example where there are 5 contiguous base pages, and we have an opportunity to convert, uh, 8 base pages into a super page. But then those 3 pages may not be used by the application, in which case we will have significant internal fragmentation. On the other hand, we could be opportunistic and create a smaller super page of size 4. And then we can say when the other 3 base pages get accessed, then we can promote this into a larger super page. So in which case we might kind of have this extra overhead of getting rid of the, tearing down a smaller super page and creating a larger super page. So there has to be some, or you could bring in pages from elsewhere in memory and then forcibly populate these pages to create a super page. So there are trade-offs in each of these options. So again, we are just discussing the problems, and then we'll see what they do for the solution. Okay. And then the third problem is that of demotion. That is, we can convert, once we have a super page, when do we demote them back down to a base page? And why would you want to demote something into a base page? Because over time, as we allocate more and more super pages, application may not need them anymore. And in which case you leave them as super pages, then it leads to significant internal fragmentation. So that's one good reason. There may be memory pressure, or the attributes of the underlying base pages may change. For example, uh, you might, some part of the base pages may be read-only, whereas others, right? So as a result of that, we will have to demote those super pages into base pages. All right. So any questions so far? I can tell you it's a lot less exciting to just talk to myself in a room than in front of a whole class. Okay. All right, so let's see. I'm gonna try to. All right, sorry about that. Just rearranging the windows here a little bit. Okay, so um, now since we are discussing the work that was done in this 2002 paper that was published in OSDI, and back then, the idea of super pages had been around for a few years, but what had happened was that people didn't have a good grip on how to best use super pages. There were various good ideas, but none of them addressed the whole problem of how to use super pages just like regular virtual memory. So uh, so one of the issues that was the issue of internal fragmentation that we've already discussed. But there is also another problem, which is external fragmentation. So if you remember from our original discussion of virtual memory, if all the base pages are the same size, let's say 4 kilobytes, right? So with regular virtual memory, your external fragmentation problem just vanishes. You don't have any external fragmentation problem anymore, because either you allocate 1 byte or 100 kilobytes, you get 4 kilobyte page granularity allocation, right? So there's no page, no memory that's wasted that cannot be allocated. But with super pages, now your external fragmentation problem comes back, because now we're going to have different sized super pages, and and now at super page granularity, you might have situations where, let's say that you need a super page of size 16 base pages, okay, 16 base pages next to each other in physical memory. But then now you can't find any region of physical memory where 16 base pages are next to each other. Okay, you might have some base pages free here, some base pages free there, some elsewhere. You might have 16 free pages, but they are not next to each other, so you can't make a super page out of those. So this is an external fragmentation problem, because even though there's enough free memory, because it's not contiguous, you cannot allocate it to a process as a super page. So this is an interesting problem, because if all the base pages were the same size, if all the pages were the same size, you wouldn't have this problem. But when you're using a mix of super pages, then the external fragmentation problem is back, right? So in order to use super pages, you need contiguous pages. So OS must restore contiguity. It must make sure that there are enough free pages next to each other so that um, so that it can allocate super pages when needed. So there's a question here from Gaurav. He's asking, can partial part of super pages be demoted based on which part of the page is used? And the demoted pages can be swapped out in the case of memory shortage. So, okay, so I'll try to rephrase the question. You're saying you have a super page, and you say, you need to demote some page. You want to swap out some pages for memory pressure. Too much memory is being used. You want to free some memory. So can you just swap out part of the super page and not swap out the rest of the super page? Um, you could. We will actually see, as described in this paper, that is what they end up doing. But we have to be careful in the sense that uh, MMU, for example, right? It just looks at a page table entry and sees whether the page is present or absent. And for Superpages, what that means is this present absent bit is 1 or 0, right? If it is 1, it means from hardware's perspective that the entire superpage is present in memory. So if your OS is doing tricks, like it's saying, okay, let me take maybe like some base pages of the superpage and swap them out. MMU doesn't know that. MMU doesn't have that extra information which part of the superpage is swapped out. So you can't, so MMU, if it gets an offset that falls into one of the swapped parts of the superpage, then it's just going to go and try to access that physical memory address, and it will easily access some other process's memory, which is not what we want, right? That would be incorrect. So we need to be very careful in that we have to first demote that super page around the base pages that we want to swap out, and then mark it as a smaller super page so that MMU isn't, it knows what we are doing. And then we can swap out those base pages that we want. I hope does that answer your question, Gaurav? Okay, so all right, great. So all right, so Jeremy has a question. Do pages that are equipped into super pages usually share attributes? For example, belong to the same process or have the same access permissions? Uh, so yeah, yes. So by attributes, we mean readable or readable, writable, executable, right? And with the, so all the so super pages are basically, they relate to virtual memory translation, right? You have a virtual page and you have a physical page. So super page or huge pages, they basically mean that instead of treating a 4 kilobyte page, now we're going to have a 8 kilobyte page or a 16 kilobyte page that's mapped to correspondingly sized physical page. So yes, all base pages would need to have the same attribute because the MMU looks at them as one page. So when there's a virtual memory access from the CPU, the MMU has to do relocation, but it also has to do protection, right? So if the access is to write to a particular page, then the permission applies to the entire page, right? So all the base pages have to have that writable permission in order for the write to go through. Likewise, if you are executing some code from a page, then MMU has to check whether execute bit is set, and all the base pages would need to have that execute permission. There is no way for MMU to do finer grained permission check. So yes, they have to share all the attributes. And do they have to belong to the same process? Yes, that's also true because virtual address space belongs to a process. The virtual memory is one of the defining characteristics of a process, right? Um, so, uh, so, so we are taking a bunch of pages in virtual address space, which belongs to a process, and mapping it into physical memory. Uh, so, um, so all the base pages in a super page should belong to a process. Now, it could be that you can share pages using shared memory between processes, but that means you're going to share the entire super page. You can't have part of a super page belonging to one process and part of it belonging to another one. So does that make sense? Okay. All right. Any other questions? Okay, so let me proceed. So as we've seen, there are like 4 problems identified: allocation, promotion, demotion, and contiguity, or reducing external fragmentation, right? So as I mentioned, these guys were not the first ones to look at using super pages. Before that, people had thought about using superpages. For example, a process could reserve a superpage, an area of memory as superpage, but they were allowed to use only one superpage, which means that you didn't have a mix of superpage sizes. Um, there were techniques which said that, all right, we could construct a super page after physical pages are allocated, but they had to move pages or copy pages over from one physical memory region to another, which added copying cost, right? So there were certain systems where you could do eager super page creation, meaning that instead of copying pages over, you could create super page ahead of time, but then applications had to do this through programming interface, through an API, or through a system call, and this was not transparent to applications, which is what these guys want to do. Okay, and then some people also did some crazy stuff, like they wanted to do hardware support. Like this, they said, okay, this contiguity requirement is too restrictive, so we're going to have super page that's contiguous in virtual memory but discontiguous in physical memory, right? And then if we just have enough hardware support, we can make this happen. And apparently somebody had proposals for doing that, and but of course, implementing it in practice probably turned out to be too complicated. So even today, we don't have support for discontiguous physical memory for a super page. And then surprisingly, everyone was so busy to creating super pages that people completely forgot about demoting them. Right? So, and really that's a problem, because if your system keeps creating super pages but never demotes them, then you're soon going to have a memory full of one huge super page, right? So it's really important to address demotion. As people say, clean up your mess, right? So, so we're going to see how they're going to solve all of these problems and provide the support transparently. Okay. So next, the paper goes ahead and talks about the design issues. Design meaning like how each of these techniques are, what are the design decisions they make, and then how they implement it. So first of all, you need to know like how big a super page do you need to create. And here they're going to use certain hints from the application. For example, if an application does a malloc operation, it says, give me an array of, whatever, like maybe, say 100 kilobytes, all right? Then you know that, okay, possibly this process is going to create some object that's 100 kilobytes in size, so it needs a correspondingly sized super page that's close to that size, right? Maybe 128 kilobyte super page. So, or you open a file, a process opens a file or memory maps it, and you know what is the size of that file. So you know that, okay, maybe I can create a super page that closely matches the size of that file. So you can use various such hints from the application to determine what is the size of the super page that you need to create in the operating system. So if you can essentially identify the memory object that the application is trying to use, and it means looking at some of the semantics of the system calls and library calls possibly that the application is making, you could guess the size of the page. Okay, and so the other rule of thumb they want to do is that they want to create super pages as large as possible and as soon as possible. They don't want to wait too long. So as soon as there's an opportunity to create a super page, they want to create it. Okay, as long as there's no penalty for wrong decisions. So they don't want to end up creating a very large super page and then the application will use only a small bit of it. Then you end up with a huge penalty being the internal fragmentation cost that you get. All right. So, so the first thing they introduce is the notion of preemptible reservation. This is the allocation problem that we're solving. So what that means is that suppose somehow magically they have this guess of what is the size of the object that the application is trying to access, whether it's an array or a structure or a file, right? Now, if application accesses this virtual page number B, then in the physical memory, let's say they know that there's going to be roughly 4 base pages in size. So now they're going to reserve 3 base pages near that physical page B as reserved pages. What that means is they're going to say these pages are reserved for that process which is trying to access that its page B. I'm not going to allocate these 3 physical pages to any other process or any other object for that matter anywhere else. Okay, so this is like reservation. Like this, I have an opportunity to create a super page of size 4, so I'm going to reserve that space and not let anyone touch it, at least for some time. So that's the idea of reservation. Okay, so what will happen if my guess is right? Then the process will soon access pages A, C, and D, and as soon as it does that, I can immediately jump ahead and convert the whole thing into a super page of size 4. Okay, so that's assuming that my guess was right. Okay, but what if my guess was wrong? Suppose that I had reserved those 3 pages and the application didn't touch the neighboring pages. So in that case, I don't want to pay a penalty. So that's where the preemptible part of the reservation comes in. Preemptible means that I can cancel the reservation if somebody else needs those base pages to create a super page. Okay, so I will give an opportunity to this process, but if this process doesn't use its reservation, then I'm going to cancel the reservation and give it to someone else after some time. So this way, say if I go back a couple of slides, in the beginning, if you notice, I only did a reservation. I did not create a super page right away. Okay, and only when the application touched the neighboring pages, at that point, I created a super page. So this is important. I made a reservation. I didn't create a super page. The super page was created only when all the base pages were touched. So this gives me an opportunity to cancel the reservation if those base pages don't get used up. Does that make sense? Any questions on this? Autumn has his hand up. So do you want to type in your question? Satrio has a question. If reservation is cancelled, then what happened to B that is already occupying the super page? Okay, so his question is, going back to the slides there. If the let me see. All right, so if you notice that we never made a super page till the neighboring pages were accessed, right? So B was there, it was marked as a base page. So it was occupying a page table entry and a TLB entry as a base page. And the operating system had marked somewhere that I'm not going to allocate the neighboring base pages to any other virtual page number other than the ones near B. Okay, so that's all. We didn't actually create the super page. B wasn't occupying a super page to begin with. It was just a base page, right? Only when the neighboring base pages were accessed, at that point, we marked all the page table entries, 4 page table entries for the A, B, C, and D. So here we had 4 page table entries, A, B, C, and D. And then the operating system then jumps ahead and marks them all as a super page, which means changes the page table entries to say these are part of super page of size 4, and then the TLB then picks them up upon the next access to the super page. Does that make sense? So it's not that cancel doesn't mean that B's content goes away. It just means that, B remains as a base page. It was never a super page till it got promoted. Okay. So, all right. So next question, allocation, right? So um, I think I discussed that a little earlier. So on one hand, we want to maximize TLB coverage, which means that we want to allocate as large a super page as possible, as necessary, but we don't want to allocate more than necessary, because allocating more than necessary would mean that we are having internal fragmentation. So for every memory allocation request, the OS would now try to find just the right size super page. And if a super page of that size is not available, meaning that you don't have a contiguous memory region for that super page, contiguous and aligned memory region for that super page, then before giving up, we're going to go and look at existing reservations and see if we can cancel some of them to create the super page request, right? So what that means is that existing reservations had a chance already. They didn't use it. They're still holding onto the reservation. So here's a new request that might increase TLB coverage. So I'm going to go back and cancel some earlier ones, right? So how does this work? So if you look at this picture, uh, for every super page reservation, the OS is going to maintain a data structure keeping track of various reservations. So here we have 3 linked lists, size one marked 1, another is marked 2, and another marked 4. So what does it mean? If you notice for the the lowest one, which is marked 1, uh, there are 2 reservations in a linked list. One is a reservation of size 4, another is a reservation of size 2. But why are they in the same linked list? The common thing between them is that if you cancel any of these reservations, you will get a base page of size 1 that's free, that can be used for the black rectangle, right? So if you cancel these reservations, then you'll get that black rectangle, which is a base page, size 1 base page, and you can use it for some other memory allocation. Okay, and likewise, if you look at the linked list mark 2, again, there are um, 2 reservations, I believe. Just one second while I manage my windows here. Okay. Um, yeah, so there are 2 reservations, and the linked list mark 2, and one of them is a super reservation of size 4, and the other is a reservation of size 8. And the common thing between them is that if you cancel these reservations, then you will get a super page of size 2, right? So the largest super page you can get out of it is size 2, because you'll see that contiguous aligned pages that are together, they're maximum size 2. Okay, 2 black boxes next to each other. You can't have a super page of size 3. So although you can see 3 black boxes next to each other, it's not a power of 2 times the base page size. So you can't create a super page of size 3. All right. So and likewise for 4, if you cancel that reservation, you can get a super page of size 4. So um, so you maintain a list of these existing reservations, and let's say you get a new memory allocation request that for which there's not enough contiguous memory available, then you would go to this list, and then you would find a reservation that matches your size, and then cancel one of those reservations in order uh, to make a new reservation for the new request. So this might like be a bit of a mind bender, but in their paper, they said the best candidate for reservation, let's say like you have two reservations in a linked list, which one do you cancel? Well, the reservation whose most recently populated frame was populated least recently, right? So, so what that means is that, you know, in every super page you have, let's say you have, like take the example of one, the very first reservation in linked list one. It has 4 base pages, and there of which three are colored green. So so of them, one of them is the most recently populated frame, right? So take that, and then second reservation, there's one that's colored green, and that's obviously most recently populated in that reservation. So you compare them, say which of those two most recently populated frames are oldest, means like least recently populated, and then that would be the candidate for reservation, for cancellation. In that reservation has been around for a long time, it hasn't used up the reservations, I'm going to cancel it and use that freed memory somewhere else. Okay. So any questions on this so far? Okay, so let's see. All right. So what we will do is go back to the lecture. All right. So see, the other thing they mention is opportunistic promotion. What that means is that, you know, here, for example, we have a reservation of size 8 base pages. But then the application goes ahead and accesses 2 base pages that are next to each other. Now, these guys said they're going to go ahead and create a super page of size 2, even though the reservation is of size 8, but the super page is of size 2. So you can get some TLB, increase in TLB coverage by creating a smaller super page. And then at a later time, if the nearby pages are accessed, then you go ahead and create a super page of size 4. And then if the next 2 pages are accessed, let's say you create another super page of size 2. So you have a super page of size 4 and size 2. And finally, when all the base pages are accessed, you create one single super page of size 8. Right? So instead of waiting for the application to touch all the base pages before you create a super page, what you do is you incrementally create super pages of the corresponding sizes as the opportunity presents. So this way you can be a little more aggressive and create additional size super pages. Okay. Is that clear? Is there any questions about that? Okay. So um, uh, it's a demotion. So now we come to demotion, and like we said earlier, that, you know, the entire super page shares its attributes, which means there's one reference bit and only one dirty bit. So the question is, how do we detect parts of the super page that are not being referenced? So why do we need to do demotion? Because sometimes we have memory pressure, meaning that, let's say 98% of your memory is used up, and you're soon going to run out of physical memory. So you better free up some memory, right? So what do? You go look wherever you can find memory that's not being used, you can kick it out. With a super page, because there's only one reference bit, we don't know which parts of a super page are not being used, right? So, um, so one of the heuristic usually means like rules of thumb. Like it's not guaranteed to work all the time, but kind of works most of the time. So one of the heuristics that these guys propose is that whenever you have memory pressure, you automatically demote all the super pages that you have, and reset their reference bit. So if I had like a very large super page, 256 megabytes, I'm going to just demote the whole thing into base pages. And then I can swap out some base pages that are, depending upon, page access references, then I can start swapping out base pages. But then as the application starts accessing certain pages, I can then re-promote the super pages back. So this way, that if some super pages that are being actively used, they will, reconstruct themselves back. Whereas others that were not being actively used, they won't be reconstructed back, right? So, this is like, like the nuclear option, right? I'm really low on memory. I'm going to like demote everybody and then have them promote themselves as per their importance. Okay, so which is kind of simple idea, but it's also easy to see why this would work. Um, so, all right. Any questions on that so far? Okay. So we're going to look at the dirty page, the role of dirty page now next, right? So now let's say that we're going to swap out a particular page, and let's say that a super page is selected in order to be swapped out. The problem is that swapping out a super page is expensive, because you have to write a lot more to the disk, and then later when you have to bring things back, you have to read a lot more back from the disk into memory. So the question is, like, could we only write down what the question that was asked earlier? Could you only swap out part of the super page that's dirty, and not swap out the rest of it? So the answer is yes, provided we can identify which part of the super page is dirty, right? Remember that because there's only one dirty bit, by default, MMU can't tell you which base page was dirty. So in this example, we have 8 base pages, okay? And the application writes to the 6th base page, okay? So if by some magic, at the time the write happens on that 8th base page, we can demote that base page. We can demote the super page, but we don't want to demote it all the way. We want to demote it just around the location of the write operation. So in this example, what we did was to demote super page into a super page of size 4, then 2 base pages, and another super page of size 2. Okay, 4, 1, 1, 2, right? And if we can somehow do this, then when it's time to swap things out, we can only swap out the dirty base page, the orange page that is dirty, that has been updated by the application, right? Uh, so this is doable, but then you might ask, but how does the OS know that an application is writing to that page, right? Because remember, when load and store operations happen from a user level process, they just happen through the MMU. MMU directly does the translation, and then the CPU directly accesses memory. You don't have to ask OS for permission for each read and write operation on the memory, right? So in this case, we want the OS to intercept the write operation and demote the super page, okay? And as we know, in order to intercept a write operation, the CPU has to raise an exception upon that operation. So for example, when the application says I want to write to it, the CPU has to say, no, wait, I have to tell the OS. Okay, so how do you raise that exception? The trick here is that we could take the entire super page when it's created and mark it as read only. Okay, so what that means is that um, if the application reads from that super page, does the load operations, everything is fine. But if it tries to write to any base page, that would cause an exception, a write exception. And then the OS won't allow the write operation to go through. It will tell the operating system. Sorry, the CPU won't allow the write operation to go through. It will tell the OS. And then the OS would say, okay, this is a write operation on a super page, so I'm going to demote it around the location of the write operation. And then once I've demoted it, then I'm going to allow the write operation to go through. Okay, so restart the write operation. So by doing this, OS can get control of the write operation and do this demotion. So this way it can accurately track which base pages are dirty. So, but then you can say, well, wait a minute, every write operation we are going to on a super page will now become expensive, right? Because every write operation will raise an exception. That's right. But then the other trick is that we do this only when there's memory pressure. Let's say that your memory usage goes more than 90%. Then the OS could say, all right, I'm going to mark all the super pages as read-only. And then from now onwards, every write operation would cause an exception. And then I'm going to demote the super pages as needed. Okay? So this is the other trick that you can do. Like, uh, uh, so, you would find that this trick of marking a page read only in order to trap a write operation, this is very common. It's commonly used in a lot of different situations. For example, uh, you might have an application for security purposes. You don't want to see that its code is not modified, by some malicious program. How do you do that? Well, you just mark all the code pages as read only, and when somebody tries to write to the code pages, then it will cause an exception, and the OS will say, aha, somebody's trying to write to a code page, and that's not allowed, so it must be something wrong going on. Okay. So, or later when we see for virtual machines for live VM migration, again, there is a need to track dirty pages, and again, it's done through the same mechanism. Mark a page read only. When a write happens, it causes an exception. Then the OS gets control and can do something about it. Okay. Any questions so far? Okay. Somebody raised a hand. Please go ahead and type your question, Aditya. Or you can just speak. I think I just unmuted you, so you can just go ahead and speak.
Hello, Professor. Can you hear me?
Yes, I can.
So, when demoting the super page, does TLB get repopulated with the base pages?
So when, yeah, that's a good question. So the question is, if you demote a super page, it had an earlier super page entry in the TLB, right?
Right.
And that entry is now stale. It may no longer be valid because OS may have gone ahead and changed the mappings of the underlying base pages, right?
Right.
So you have to invalidate the old entry in the TLB.
Right.
Then you have to also um, so if the OS has the ability to insert individual entries in the TLB like it did in the alpha architecture, then it could certainly do that. But you
Okay.
could just leave the application to incur a few TLB misses and bring in the translations that it wants. Like it may not want all the base page translations. It may need only some that it's trying to access. So you can let the memory accesses go through and the necessary translations will come in automatically.
Right. And if there is no place in the TLB, then it will be there will be misses after those, right? TLB misses.
If there is no space in the TLB, then some kind of cache eviction algorithm will kick in, which will evict least recently used cache entries in order to bring in the current memory accesses.
Okay. Okay.
Right.
Yeah. Thank you. Thank you, Professor.
Yeah, that's right. So I mean, it again depends on the processor architecture, right? But if there is a TL, if the entry is not there in the TLB, it will cause a TLB miss. for alpha, like architected TLB case, for alpha architecture, for example, the OS will be allowed to decide which entries come in. Whereas for architected page table like x86, there will be some automated mechanism to, some cache eviction and repopulation algorithm to bring things in.
Yeah. Okay.
All right.
Thank you, sir.
No problem. Okay. Any other questions? All right. So, how are we doing with time? Okay, 5:40. So I'm not going to give a 2-minute break this time because I have no way to know when people are back. So hopefully we will finish early, and then we'll just stop with one lecture today. All right. So the other issue, fragmentation, we talked about this a little bit earlier. That the in order to allocate a super page, you need contiguous memory that is free. And over time, if you're going to allocate different size super pages, then memory is going to get fragmented, right? So what you need is some contiguity restoration technique. What that means is that periodically you have to maybe one approach is that you could take all the allocated pages, move them to one end of the memory so that the other end is all free, right? And it's all contiguous. But that's kind of expensive because it means you have to copy memory from one region to another region, right? And copying is always not a great idea. The other approach is that when normally when you do page replacement algorithm in the operating system, usually these algorithms are based on least recently used, like LRU algorithm, meaning that if the page hasn't been used for a long time, then I'm going to free it up or swap it out. But they say you should use one more criteria, which is that if I free up a particular page, would it increase the contiguity of free pages, right? So if I have two pages that are equally eligible to be swapped out or freed up, then which one should I choose? Should I choose this or that, right? You should choose one that would give you more contiguous pages. If I choose this, I get 4 contiguous base pages. If I free this, I will get only 2. Then of course I will choose this one, which gives me 4 contiguous base pages, right? So so you can use contiguity as one more criteria in deciding which pages are most eligible to be freed. And then there is another issue which is to do with wired pages. What does that mean? Usually when wired usually means that to pin something. So meaning that, for memory context, it means that if you allocate a page, normal pages could be swapped out to the disk. But with wired pages are some special pages that are marked saying, are telling the OS, don't swap these out. They're very important. I need them in memory all the time, right? Now, why would you want to do this? Like for DMA operations. See, we know that IO devices like disk or network card, they have the ability to directly access main memory to perform IO operations. Like network card gets a packet, it can directly write that packet into a pre-decided location in the main memory without asking the CPU. So this way CPU is not involved in each IO operation. So DMA is very important. But in order for IO devices to directly access a memory region, there has to be some guarantee from the OS that those pages won't be swapped out while the DMA operation is going on. So in traditional operating systems where it's not super page aware, these DMA pages that are marked for DMA, these wired pages could be all over the physical memory. Some could be at the low end of the spectrum, some could be in the middle, some could be at the end. They could be scattered all over physical memory. And the problem is that if you have wired or pinned pages all over the physical memory, then it breaks the contiguity of free pages. You will have these small pockets of free pages where you can't allocate them as a large superpage. So, so in there, they observed this problem in their implementation, and then they suggested a solution, which means that they say if you set aside a part of physical memory which is only used for DMA, right? And that way the rest of the physical memory will be free for use in superpages. So this is called clustering the wired pages, means all the wired pages are together in one region of physical memory. And the free memory is for everyone else to use, okay? So by doing this, they maintain contiguity, and that's obviously, beneficial for superpage allocation and reducing fragmentation and superpage granularity. Okay, any questions on that? Okay, so we will go back to the slides. So for any research proposal, it's not, whenever you do research, so some of you may be doing, it's not good enough to say, hey, we have a great idea in here, so you do it, we build a prototype. But it's not enough to build a prototype, you have to show that it works. And you actually get the performance that you promise. Right? So these guys did the same thing. Again, this was about 18 years ago, right? And when they did the project and then they published their paper in 2002, so they implemented their system in the FreeBSD operating system, which is another very popular open source OS back then. FreeBSD is still around, except that now Linux has become more popular. But FreeBSD came from Berkeley, and one of the things was it ran on these alpha processors, and alpha processors, they used alpha system with alpha CPU on it. Of course, you can see the specs look old, but for that time, this was kind of a high-end system. And in there, they had the processor supported 8 kilobyte, 64 kilobyte, 512 kilobyte, and 4 MB superpages. As you can see, there are two TLBs, one for data, one for instructions, right? And each of these TLBs have 128 entries. So as you can see, there's not like a whole lot of space in the TLB, but then we can increase the coverage by using superpages, okay? So they ran unmodified applications, and so what kind of applications? They talk a little bit about that in the paper. Usually when you run do performance evaluations in your research, you have to use something called benchmarks. Benchmarks are common programs that everybody uses for evaluation. They're widely accepted. And that way, if somebody gets some performance number, you can compare it against the numbers you get. Everyone is running against the same baseline benchmark, right? So and then you can see who does a better job. So Spec is an organization that creates a lot of these benchmarks, CPU, memory benchmarks, and so forth. So they ran something called Spec CPU 2000 benchmarks, which has integer and floating point programs to run. And then they run a bunch of other numerical benchmarks like fast Fourier transform, matrix transposition, and so on. And as you can see, they did really, went out of their way. They tested a lot of 35 benchmarks in all. So it's not enough to just run one program and say, hey, for this program, my system works well, so I'm going to call it a day. No, you have to run it across a bunch of workloads and then show that where your system works and where it doesn't work, which is what they did. Okay. So this is kind of a summary of their results. So they got like about 11.2% improvement for integer Spec CPU 2000 benchmarks, 11% improvement for floating point. For like things like fast Fourier transform, they got 55% improvement, which means that this was a benchmark that was causing a lot of TLB misses, and by using superpages, they were able to reduce the TLB misses and increase the coverage. Okay, and for something like 1000 cross 1000 matrix transposition, they got 655% improvement, right? But they just don't report their best numbers. For example, for for the floating point benchmark, in some cases, they say that they lose some performance, like some benchmarks did minus 1.5% worse, right? So again, it depends upon the behavior of the workload, the memory access patterns, as to how much improvement you get. So the point is, like, to be intellectually honest, to say that, here's a system and we know where it works and where it doesn't work. And that's useful because somebody wants to use your system for their workload, then they will know whether your solution is a good choice for that or not, right? But generally they said, for 8 out of the 35 benchmarks, they got more than 30% improvement. So, which is like a pretty good number, right? So um, here's another benchmark. So it's not enough to say that we get improvement. We also need to say, compared to existing solutions, how do we do? Well, existing solution meaning, in this case, the solution would be, what if you use only a single superpage size? So you go through this trouble of implementing, preemptible reservation, opportunistic allocations, speculative demotions, and fragmentation control. It's a lot of changes to the core memory management operations of the OS, right? And is it worth all the trouble? Maybe I could have just used a large superpage size for everything, not have to change any of this OS stuff, and I could still get some improvement, right? So then I don't need your system, right? So they measured that also. So they say, okay, what if all the pages were 64 kilobytes, or all of them were 512 kilobytes, or all were 4 megabytes? And then finally, what if you use a mix of superpage sizes, which is what their system is needed for, right? So you can see that, for fast Fourier transform, if all your pages were 4 megabyte size, you would get 55% improvement. And with their system, with a mix of superpage sizes, they still get 55%. And you can say, well, look, your system, we don't need your system. We just need to set our page size to 4 megabyte, right? But then there's another system called Galgel. I'm not sure what that does, but apparently by mixing all the superpage size, they do 29%, versus if you just use 64 kilobyte or 512 kilobyte, you will get 28%. So, that's, you just get a 1% improvement over existing solution, right? For MCF, they get like 68%, which is better than using any single superpage size. So they will say, all right, there's only one application where a mix of superpage size is useful, right? But another thing to note is that they never do worse than any of the single superpage size solutions, which means that if you use their solution, then most of the time you will do at least as well as any single superpage solution. And you won't have to guess what superpage size to use. Simply use their system, it will find the correct superpage size and use it for you, right? Or if you need a mix of superpage sizes, it will find it for you and use it for you. So that's a part of the transparency, that application programmer doesn't have to guess what superpage size do I need. The OS does it for them. Okay. So uh, so then there's conclusion. They basically say what they learned, and they show a mechanism by which OS can provide transparent support for superpages. And then one of the things they learned through their experiments and evaluations and implementation is that you need contiguity restoration. If you're going to use superpages, you are reintroducing the external fragmentation problem at the superpage granularity, not at the base page granularity, but at superpage granularities. So you need some mechanism to restore contiguity, because otherwise, over time, your memory is going to get fragmented increasingly, and you're going to lose the benefits. And they also show that for many applications like MCF, for example, having multiple superpage sizes is important, because that way you can just allocate superpages that fit the object or memory allocation size, and that way you can reduce the internal fragmentation required. Okay. There is a lot of information. Of course, this seems like an old paper, but then it's very fundamental also. Many of the ideas are still making it into modern implementations of Superpages. Linux still has somewhat rudimentary support for Superpages. People are still figuring out how to make it mainstream in mainline Linux. But if you look at the Wikipedia link, for example, it has really useful information, interesting information if you're curious to learn more. All right, so that's all I have. Does anyone have any questions about any of the stuff we discussed so far? You can raise your hand, I can unmute you. Any comments? Any comments about how this online format is working? That you have any suggestions? No questions. All right, looks like so we will end a little early, right? And then next time on Wednesday we will have the same thing, completely online class. It's good, like we have 49 participants. Hopefully everyone is paying attention, right? So and again, it would be good if we have like we had quite a few questions, but it'll be good if we can have more questions in the future. That way I will feel a little less lonely here. You have a question, but not about the lecture. All right, go ahead. Yes, key 45 peers. I'm not sure who this is, but please. When do we get grades for the midterm? Oh, sorry, this is okay. All right, Bobby. Yeah, I have to release the grades. We had to move online, and things got crazy, so that got put in the back burner. The grading is almost done. I'm the bottleneck here, so I just need to go over the grades one time and then release them. Okay, it'll probably take me an hour, so I should do it today. Yeah, thanks for reminding me. Okay. It looks like the lectures are being recorded. Are they going to be posted somewhere? Um, yeah, let me check what is the quality of the recording. Okay, and then we will try to post them. I think we'll have to convert it into YouTube or something, because I don't think I have storage space on. I can't put it on GitHub, which is where the class slides are. They won't give us that much storage. So we'll see. We'll try to make it available. We'll try our best. Okay. Yeah. Any other questions? Could you post this slide that was the alignment exam? Okay. Sure. Yeah, I would yep, convert this into a PDF and post this on the course website. Thanks for telling me that. Yep. Okay. Any other questions? Okay. So great. So I think that's the end of the class, and feel free to email us or whatever. If you have suggestions on how we can improve this online thing, let us know. Thank you. Yes, you all, everyone have a safe rest of your semester. Thanks. Take care. This is the end of the class. Bye.